this is more important and more interesting than plasmonic waveguides. All right, so metamaterials always begin with this slide, which is the epsilon, which is the electric permittivity, and the mu, which is magnetic permeability of the existing materials. And then here you can see epsilon positive and mu positive is most dielectric material occurs. And then here epsilon negative is possible for metals, right? That's what we learned. And what about epsilon positive but mu negative? Well, there is some possible cases, but it's only in a very low frequency. But like in high frequencies, at high frequencies like optical frequencies or infrared, there's no material exist in this regime. And here, absolutely no material exists, no matter what. So our question is, can we do some, by using a nanophotonics, can we create some artificial material that have electromagnetic properties not found in nature? So there are two possible cases. One is negative index, like epsilon negative, mu negative, or hyperbolic case, like epsilon in one direction is positive and epsilon in the other direction is negative. So in this lecture, I try to explain how can we achieve these strange electromagnetic properties by using nanostructures, and what's the applications of those metamaterials. So if I just begin with the term itself, meta means beyond, okay? Materials is just materials. So it's like a material beyond the naturally occurring material. So what the main idea is simple. Natural materials are made of atoms, right? Size of a few angstroms. Okay, but as I probably mentioned earlier, if you compare the size of an atom with a wavelength of electromagnetic wave that we are interested, which is about like 1 micron, it's much, much smaller than the wavelengths, right? But it's kind of too small compared to the wavelengths, so that we can probably fit in some larger object, like much, much larger than atom, but still much, much smaller than the wavelengths of light. So let's say you can think of like 100 nanometer to 10 to few 100 nanometer structure, right? Then in the perspective of light, they cannot distinguish whether such material is made of a middle scale nanostructure or made of a pure atoms, right? Because anyway, it's much smaller than the lambda, so that they cannot distinguish. It's way under diffraction limit. So here's basically the room for engineering, right? We just create a small nanostructure of size about 10 to 100 nanometers to basically deceive light and create non-intuitive electromagnetic properties. So how we do that? So before we talk about details, we want to first talk about mixing two material, okay? Because I want to mention that, let's think about this case. If we mix two materials, having one material having permittivity epsilon 1, the other material having permittivity epsilon 2, then what would be the permittivity of the mixed material? Would it be just epsilon 1 plus epsilon 2 divided by 2? if you actually look into it, you will realize that it's not that simple. It's not like, you know, just let's say you have a volume fraction of epsilon1 material F1 and volume fraction of epsilon2 material F2, then epsilon3 is F1, epsilon1, F2. So this would be the simplest answer, right? This would be the most intuitive answer that you have, which is not true. Okay, so this is true for certain cases, but it's not always the case. And there are many ways of treating this composite media. So there are Maxwell-Garnett theory, where you have a host material and the incursions can be separated clearly. In that case, you can basically assume your incursions to have a spherical shape, and then you can come up with a kind of effective medium theory. And second way is like called a Brueggemann case. In this case, epsilon1 and epsilon2, it's not like host and incursion. It's like kind of mixed. There's no way that you can distinguish what's host and what's incursion. Okay. And you can also think about this layered material case, like epsilon1 and epsilon2 are just layered in an ordered manner. Okay. So one difference here compared to the 1D photonic crystal is that in 1D photonic crystal, the periodicity is similar to lambda. It's at least similar or like at least comparable to lambda. What I'm talking here in layered medium is that the period is much, much smaller than lambda. Okay, so that we don't have any kind of, you know, how can I say? Bloch theorem induced, you know, a band structure, because A is much, much smaller than lambda in this case. So what's happening? Let's look at the Maxwell-Garnett and Brueggemann case. And as I said earlier, in Maxwell-Garnett case, you have host material and incursion, and incursion forms a closed volume. Okay, in this case, you use this equation to get an effective permittivity. I don't want to explain in detail. If you're interested, you can just look at this literature. And the Brueggemann case is different. Brueggemann case, you cannot distinguish what's host and what's incursion. In that case, you can calculate the effective permittivity using this relation. I mean, these two relations are very different. But one thing you can realize is that here, both of the case, you see epsilon effective plus 2 epsilon background, epsilon effective minus epsilon background, which is very familiar to you because you saw this in a localized plasma resonance case, right? When we calculate alpha, the polarizability of localized sphere, you encounter the same mathematical form of these permittivities. So they are related, right? You basically approximate this situation to a spherical incursion, and here too. Okay, so it's how it's related. But if you need a full derivation, just look at this paper. So what I want to say is this one, the layered structure. Okay, so here you have epsilon A and epsilon B is stacked in an interchange, this alternating manner. And here, the permittivity along this direction and the permittivity along that direction are very different. Why? You can think about like using this as your insulating material, dielectric material for your parallel plate capacitor, for instance. Okay, so if your electric field is perpendicular like in this direction, perpendicular to the optical axis. So this is optical axis. So if your electric field is perpendicular to the optical axis, where electric field in this direction, then what happens is that you're basically putting two metallic plates here and there, which is a bunch of parallel connection, right? Bunch of parallel connection of capacitors, right? Each has a permittivity of epsilon A and epsilon B. So in that case, if you calculate the total capacitance is just sum of all these partial capacitances. So in that case, the permittivity, effective permittivity, if you calculate it, it's like this. It's just the same as the fraction of material A times epsilon A plus fraction of material B times epsilon B. Okay, but if your electric field is polarized in this direction, then the situation is like you have a materials, parallel plate capacitors in series connection. So if you have series connection of parallel plate capacitors, then total capacitance can be calculated by this, right? 1 over C is 1 over CA plus 1 over CD. And if you do so, what you realize is that your permittivity should satisfy this relation, okay? So what this tells you is that if you have a material of layered medium, your permittivity varies a lot depending on the direction of the electric field, okay? So that you can create anisotropic metamaterial. Okay, so why this is interesting? Well, you can think of many different things. Like for instance, if your electric field and magnetic field, if you look at thinking about the wave equation, so electric field. So ordinary waves. What you call ordinary waves is that electric field is perpendicular to K and also perpendicular to the optic axis here, this axis. Then electric field is aligned with D field, okay? Because there's no problem in calculating, because the same permittivity epsilon perpendicular is applied in the conversion between E and D. But like in the other case, what is called extraordinary case, in that case, H field is perpendicular to K and the optic axis, so that electric field is basically having a in-plane direction here, right? So in that case, as I said earlier, the permittivity is very different for the electric field along that component and electric field along this component, right? So different permittivities applied for this component and that component of the electric field. And because of that, electric field and D field are not aligned. And also, this dispersion relation, the omega and K relation is very different. So here they use different permittivity. And probably even so far, you don't know why this is important, right? I mean, this is strange, but why this is important? But this is important because people figured out that it is actually possible to make these two components, epsilon perpendicular and epsilon parallel, to have different sign, not just simply different, not just having different values, but having different sign, okay? And if these two have different sign, then interesting thing happens. Like if you think about this relation. So let's say this is K parallel, perpendicular and K parallel. And then, so in typical materials, if you draw a isofrequency surface, like a fixed omega surface, this is a fixed number. So it's always like a circle, right? Something squared plus something squared is constant number, gives you a circle, right? And then if in a anisotropic material, epsilon's perpendicular and epsilon parallel are different, then but the same sign, then what you have is ellipse in an isofrequency surface, right? And now if these two have different sign, then all of a sudden this relation becomes hyperbolic, like this, right? It's not an ellipse anymore. It becomes a hyperbola, right? So why this is important? Why? Okay, so you can understand that, okay, this is strange, but why this is important? The reason this is important is because, okay, so there are many ways of creating, hyperbolic isofrequency surface using metallic nanowires or meta cylinders looking like this. Oh, by the way you obtain a positive and negative permittivities is basically using one of the material to be insulator, which has positive epsilon, and the other material to be metal, which is negative epsilon. So positive negative combination. And then if you make these two numbers in a gentle manner, then you can make one of these to be negative and the other of this to be positive. It's always possible to do that. Okay, so now let me tell you why this is important. This is important because you can use this to create what is called hyperlenses. So what is hyperlens? In order to understand that, let's look at this equation. This first, this is a normal case. So regular material at a fixed frequency, Kx and K, well, here Kr and K theta have always a circle in a far field. So what does that mean? Is that, if your feature have a characteristic frequency, characteristic surface frequency larger than this range, it cannot be, how can I say, imaged. Do you understand what I'm talking about? So let's say you want to, it's related with a diffraction limit. So if you have a feature that is smaller than λ/2, and then thinking about doing a Fourier transform of this. If you want to do a Fourier transform of this, you need a high K component. It's necessary, right? In order to describe the situation. If your Weir space image has a high frequency or fine feature, you must have large K vector in order to describe it. But because of this, your K vector can only have a certain range, right? From, like in this case, from omega plus minus. This is the range that you can have. And that basically gives you a diffraction limit and also the limit in the image resolution in all optical imaging system. Okay, so how can we break this limit? By using hyperbolic metamaterials. So if you use hyperbolic metamaterials, like in this case, now along the theta direction, the K vector range becomes infinite, right? So it's not like having limited K vector range, but it has like unlimited K vector range in the hyperbolic medium, so that no matter how fine your image is, there are always, you can always find an associated K vector that can propagate in the medium. So that like in here too, you can have a basically sub-diffraction limit imaging by using this hyperbolic metamaterials. So up to this point, it may sound like this is like a magic, but the problem is, of course, hyperbolic metamaterials are lossy because we have metal, right? So that in practice, its propagation length, the wave cannot propagate forever, but like it decays after a few oscillations. So its actual application is kind of limited. But anyway, this is the in principle. If you have a hyperbolic metamaterials, you can create hyperlens that can break the diffraction limit. So that's the implication of the hyperbolic metamaterials. So you can actually look at the experimental demonstrations. So this paper, published in 2007, uses this alternating layers of here silver metal, and then alumina, which is a dielectric. So silver dielectric multilayer, and by using this multilayer, they could resolve something that is much closer than the diffraction limit, like 20 nanometers, which is a sub-diffraction limit, can be resolved by using this one. So this paper also got a tremendous attention at that time. Okay, and then you can also do a negative diffraction, but I'll probably explain this later in the next lecture. Okay, so this is all I want to say today.